Let's look again at a round object placed on an incline. Now this incline has been supported under this edge by a couple of dominoes and nothing under this edge. If I release the ball from any point on this incline, it's going to accelerate down the incline. So the ball has an acceleration along this incline. If I release it from any other point, it speeds up at about the same rate. It didn't there just a minute ago because I think I made a little indentation, steel ball on styrofoam. But wherever I do this, the ball will tend to accelerate at the same rate, tend to gain speed at the same rate. Its velocity will change at the same rate everywhere on this incline. I'm asserting that comes from physics and comes from certain types of analysis that we're not going to talk about in a calculus class, except to, again, simply assert them. Now, if I start this ball rolling in this direction, what's going to happen? It follows a curved trajectory. It accelerates in this direction, but if you noticed, it didn't slow down much in this direction. And theoretically, if we have a perfectly smooth ball, perfectly smooth plane, with no friction, the ball won't slow down as it moves forward. Now, it'll move forward at a constant rate, but it'll speed up in this direction. And of course, if I roll the ball, start the ball up from this direction, it's going to slow down before it speeds up and comes back. When it's moving in this direction and slowing down, its velocity is changing in this direction. So it's accelerating in this direction. And the acceleration of the ball from here to here and back is really always the same. It's always accelerating at the same rate in this direction. The velocity is always changing at the same rate with respect to time. Now, let's use a vector function to analyze that sort of a situation. What I've just said is that the ball has an acceleration. If this is the I direction and this is the J direction, the ball has zero acceleration in the I direction, but it has a constant acceleration in the J direction. Now I've used the letter G to indicate that acceleration, because when I wrote this a few minutes ago, or a couple of hours ago, I didn't anticipate using that incline. So I'm going to say G sub C, just to separate it from G. G is the standard symbol for the acceleration of gravity, and this is just a component of G in the direction of the incline. And again, don't worry about the reason for that or the physics of it unless you happen to be a physics student. Okay? Now, I want to analyze the motion of this ball in general. So I'm going to say the ball has an initial velocity, which is a vector, v, and we're going to let t equal 0 be the time, the clock time when I release the ball. Now I can release that ball in the horizontal direction, but I can also release it so that it has some vertical motion. If this is vertical and this is horizontal, I can do this. Okay? I can start that ball off at an angle. Now, I'm going to let theta be the angle at which I start the ball with respect to horizontal. We're going to have to change our perspective a little bit, because when I rolled the ball, I was using the direction, this direction as the x direction, this direction as the y direction. Now I'm going to kind of turn the coordinate system around to where the x is here and the y is here. But we can understand that if I start a ball off with a velocity v naught at in a direction that makes some angle with the x-axis, then that velocity can be expressed as a vector, which I'll call v of 0, and v sub 0 is just a scalar. It's a number which we identified with the speed. v0 is the speed multiplied by the cosine of theta. That gives us the component of the velocity in the x direction, so that this is v0 cosine theta. And I could say that's the x component of my velocity. X v0 cosine theta times I would be the x component of my velocity, and v0 sine theta j would be the y component of my velocity. And the cosine and the sine should be very obvious from conventions and from the position of the angle within this right triangle. Okay, so our situation is therefore a of t equals 0I minus g sub c j, and v of 0 equals v0 cosine theta I plus v0 sine theta j. We know that acceleration is what we mean by the derivative with respect to clock time of the velocity, so that a of t equals dv of t dt. If we simply assume that we can apply the same principles to vector functions that we can to their components, we conclude that v of t is an integral of the a of t function. And it's very easy to do this integral. We simply write out what a of t is. It's the integral of 0I minus g sub c j dt. Okay? Now, the integral of 0, an antiderivative of 0, is any constant. So this is the integral, well, okay, I didn't mean to write the integral sign, but okay. I'm going to break this into the integral of 0I dt minus the integral of g sub c j dt. Okay, antiderivative of the 0 function is just any constant function, so this will be c times I. Let's call it, okay, we'll stay with c. We'll use c1. c1I, and an antiderivative of g sub c would be g sub c t plus c1, integration constant, times, call that c2, times j. So that our integral of the a of t function is just, I'm going to write it this way, c1 I plus c2 j. Now c1 and c2 are arbitrary constants, and it's negative c2, but an arbitrary constant will absorb the negative in a way that you should understand. And we then have gct multiplied by j. And I'm going to call this vector here c, just a constant vector. I'm going to c1i plus c2j is just a vector with arbitrary components that happen to be constant, so that this can just be represented by a c vector plus g sub c t j. Now, c was a bad choice for the subscript. Remember, that subscript doesn't really mean anything and doesn't have anything to do with this c. Matter of fact, since this was an arbitrary choice, I'm going to change that c to a d throughout. So call this g sub d, and hopefully we won't run into any confusion with the notation. Okay. So where we are right now is the motion of this thing is characterized by this acceleration, and this acceleration gives us the integral, which is the velocity, and the velocity comes out to be just a function, constant vector, plus a constant times t times j. And that should be minus. Those should be minus because I had a minus here. I got careless with my notation. going to have to try to fix that. Let's put something down there to obliterate my error and find something else to put here. How about the corner of this magnet? Okay, now the expressions look sort of like they should.